Good morning, students. In this video we are going to solve problems on singly reinforced beam. So let us take this problem. We have a rectangular beam of size 230 mm wide and 530 mm effective depth, which is subjected to a bending moment of 88.5 kN at working loads. Find the steel area required. So how much area of steel is required, that has to be calculated. So the grade of concrete is M15 and Fe415 steel. So let us calculate now. So what they have asked is they have given the bending moment and they have given the size of the beam. We have to calculate how much steel is required. So what happens is that if you take in the previous semesters also you have calculated the bending moment. After calculating the bending moment, what we have to do? We have to find out the area of steel. How many bars we have to put? That is what we have to done. So that we'll try to do it in this problem. So the width of the section is 230 mm. Effective depth, small d, it is 535 mm. Next is they have given working loads. 88.5 kN is the working load. But we will try to calculate for always factored bending moment. So we'll apply a factor of safety. So we'll apply a factor of safety of 1.5. So therefore we'll try to calculate the factored bending moment. So that is equal to 1.5 times of 88.5 kN. We'll apply a partial safety factor of 1.5 to the load or that moment. So if you multiply, you'll get answer as 132.75 kN. So for this moment, we will try to calculate what is the area of steel required. So FCK is 15 and Fy is 415 Newton per mm square. Then next is we will try to calculate the limiting moment. From this we can tell whether the beam is over reinforced or under reinforced section. So limiting moment you can calculate the formula, that is 0.138 FCK BD square. So that formula also you can use, or you can use 0.36 XU max by D 1 minus 0.4 to XU max by D into BD square FCK. So if you simplify this, you will get that for steel grade of Fe415 you will get it as 0.138 FCK BD square. So if you substitute, you will get the answer. Or if you simplify this also, you will get the answer. So XU max by D, already we have seen the previous table, XU max by D value is 0.48. 0.36 we have, XU max by D value is 0.48. Already I had shown in the previous video also how you will get this 0.48. In the IS code they have given. So 0.1 minus of 0.42 we have. The next is XU max by D, it is 0.48. B value is 230 mm. D value is 535 mm square. The next FCK is 50. If you substitute, you will get answer as 136.24 kN. This is the limiting moment we have. Our factored bending moment is 132. So 132, it is less than 136. That is Mu is less than Mu LIM, limiting moment. So therefore beam is under reinforced section. Next is we will try to calculate area of steel. So already this formula also they have given in the code book. So in the previous problem we had seen that area of the steel was given. We had calculated the moment. Now in this problem what happens is that now this moment is given to us. Based on this we have to calculate what is the area of steel. So moment is 132.75 into 10 raised to 6. We will try to keep it in Newton mm itself. 0.87 we have. F of I is 415. Now AST is nothing but this has to be calculated. Keep it as it is. Depth is nothing but effective depth, that is 535 mm. So 1 minus of F of I is 415. AST has to be calculated. BD FCK also we know. So that will substitute. If you simplify this equation, if you simplify this 132.75, it is as it is. If you simplify this 0.87 415 AST multiplied by this 535 multiplied by this one, if you simplify, you will get this value. Then next is this 0.87, this multiplied by this, you will get 43.43 AST. So you will have AST square. So now this is the equation we have. AX square plus BX plus C you can have. So you can simplify this equation and you can calculate the value of AST. AX square plus BX plus C. So this directly you can solve it in calculator and you will get the answer. That is, AST required will be 850 mm square. This much area of steel is required. Or otherwise you can see this formula also, you can substitute here and you can calculate. So this formula is 50 into 1 minus of square root of 1 minus 4.6 into mu divided by FCK BD square divided by F of I divided by FCK. So 50 we have. So 1 minus square root of 1 minus of these values we have. So 4.6 we have. Mu value already you know. FCK is 15, B is 230, D is 535, Fi is 415, FCK is 15. If you substitute, you will get percentage of steel as 0.692. This is not PT, nothing but percentage of steel. So how do you calculate percentage of steel? That is equal to AST divided by area of steel divided by BD multiplied by 100. BD multiplied by 100 we have. So now what happens is that we have calculated this PT, we know this B value, we know this D value. Next is only unknown will be AST. So therefore AST will be equal to, you cross multiply this PT, that is 0.692 multiplied by BD. BD we have, that is B is 230, D is 535. This 100 will come down in the denominator, that is 100. So based on this also you can calculate, that is you will get answer as 851 mm square. Either you can calculate in this way or in the previous way what I had shown. It is one and same itself. Next we will go to the another problem, that is design a singly reinforced rectangular beam for an applied factored moment of 120 kN meter. Use M15 grade concrete and Fe415 steel. So in the earlier classes we used to calculate like shear force, bending moment and all. So after that what we have to do, right? So after that what we have to do is that we have to design the member. So now how to design the member, that is what we are going to see it that is what we are going to see in this problem. So our moment is like 120 kN meter now. So for this what we have to do is that moment is 120 kN meter, FCK is 15 and steel is 415, therefore Fi is 415. So design a section means what we have to do is that we have to, if you take one beam, so now this is the beam we have now. So what should be the width of the section? What should be the depth of the section? And what reinforcement we have to put? What reinforcement we have to put? These three things we have to calculate now. Design means these three things we have to calculate. What is the width of the section? What is the depth of the section? And how many bars we have to put? That is what we have to calculate. So now how to calculate? So let us start. So first what we will do, we will assume the width of the beam B is equal to 230 mm. So how we have fixed this width of the beam? So usually what we do is, whatever is the width of the wall, so that width of the wall we are going to fix it as a width of the beam. Why? Because the wall and beam they are going to flush. So therefore we are not going to see any offset in the rooms. So therefore what we do, we are going to fix the width of the beam that is equal to width of the wall. So usually we have 9 inches wall, that is 230 mm. So therefore width of the wall is 230 mm. So therefore what we will do, we will assume width of the beam as 230 mm. Next comes is we have to calculate the depth now. So how to calculate the depth? So what we will do, we know the limiting moment formula, that is for Fe415 it is 0.138 FCK BD square. So for mu, right? So now what we will do, we know the moment now. We know the moment, this moment we know. So what we will do, we will try to calculate it in reverse way. That is, we know the moment now. So for this limiting moment, what is the depth required, that we will try to calculate. So what happens that if you provide this much depth, our section will be safe, our section will be under reinforced. So we are calculating in reverse way now. So moment is known to us, we are calculating the depth for a given limiting moment. So therefore 0.138, FCK is 15, B is 230, D is unknown to us. So we'll bring all these terms this side. Therefore mu we have divided by 0.138 FCK B. So 0.138 FCK B. So this will come this side. So therefore this will be square root of. So therefore D will be equal to this. So if you substitute and if you calculate, you'll get answer as 502 mm. So this much is the D required. This is the depth required. So if you provide this much, our section will be under reinforced section itself. So what we'll do, D required is 502 mm effective depth. So what we'll do, we'll assume effective cover of 40 mm. So if you see, we'll assume 40 mm. So therefore overall depth capital D will be equal to 502 plus 40 mm. So therefore it will be 542 mm. Approximately it is 542 mm. So what we can do, we can assume it as 550 mm. 550 mm. So what happens is that, for example, if this is the beam we have, so we will provide the bar somewhat like this. So the small d what we had calculated, it was somewhat like this. This is nothing but the small d we have. So we had assumed this effective cover. Effective cover is nothing but from this bottom of the reinforcement to the center of the steel. So we have assumed this cover as this effective cover as 50 mm. So therefore this total depth will be equal to, what we have done is, at the end we have assumed it as 550 mm. So 550 mm is the overall depth. So if you want to calculate now effective depth, if you use 20 mm dia bars, for example, now this is the beam depth we have. So what we have done is that we have taken total depth of 550 mm. We have taken total depth of 550 mm now. So these are the bars which are being placed at the bottom. So what we'll do is that we'll assume that these bars are 20 mm dia. We'll assume that these bars are 20 mm dia and this cover has to be taken. So now this depth has to be subtracted so as to get the effective depth. So what we can do, this clear cover we can take it as 25 mm. Then next this bar we are going to take it as 20 mm. So center means 10 mm. So 25 plus 10, 35. So 550 is the total minus this 35 mm. If we are going to subtract, you will get this remaining effective depth. So therefore if you see, so effective depth will be equal to 550 is the overall depth minus 25 mm is the clear cover minus 10 mm. Why? Because we have assumed 20 mm dia bar. So center means half divided by 2, 10. So therefore effective depth will be 515 mm. So based on this effective depth, if you calculate the limiting moment, that is 0.138 FCK BD square, so you will get answer as 126.27. Or another thing we had seen, that is QLIM into BD square. So that also if you simplify, you will get this itself. So this value also we had shown you in the table. Otherwise what you can do, you can use 0.138 FCK BD square. So you will get limiting value as 126.27 kilonewton meter. So our moment, it is less than limiting moment. So therefore our section is under reinforced section. Then next is we'll try to calculate the area of steel now. So now what happens that, again same formula, we know the moment. Now we have to calculate the area of steel. So other values already we know. We know F of Y, we know D. Everything we know except this AST. So further if you substitute, mu is equal to 120 into 10 raised to 6. 0.87 we have, F of Y is 415, AST I have kept it as it is, effective depth is 515, 1 minus of AST, keep it as it is, F of Y is 415, FCK is 15, BD is 230 and 515. So further if you simplify, you will get answer equation as AST square minus of 4282.67 AST plus 2.763 into 10 raised to 6, that is equal to 0. That is AX square plus BX plus C. You have to calculate the value of X in that equation. So directly in the calculator you can calculate, that is you will get answer as AST is equal to 791 mm square. 791 mm square. So this much area of steel is required. So now how many bars we have to provide? What should be the diameter of bars? So that has to be calculated. So what we can do is that assume that we will use 16 mm dia bars. 16 mm dia bars. So what is the area of one bar? If you want to calculate, pi by 4 into 16 square. 16 square. 16 square if you do, you will get area of one bar as 201 mm square. So 201 mm square is for 791 divided by 201 if you do. So you will get approximately 4 numbers. If you divide this, you will get 4 numbers. So what we can do, we can provide 4 bars of 16 mm dia. We can provide 4 bars of 16 mm dia. So for example, if you don't want to provide 16 mm, if you want to provide 20 mm dia bars. So what you can do, you can calculate area of one bar, pi by 4 into d square, that is 20 square, you will get 314 something you will get. So 791 divided by 314 if you do, you will get approximately 3 numbers. If you want, you can provide 4 numbers of 16 mm dia bars, or if you want, you can provide 3 numbers of 20 mm bars. So both the ways, if you provide, it is correct, no problem. Either this or this, whichever you feel comfortable, you can provide. So again, it depends upon the structural designers. So they are going to depend upon the structural designers. So they are going to decide on their own and they are going to fix the bars. So ultimately, if you see what we have done, we have designed one beam, rectangular beam of width, so that is 230 mm. Depth is overall depth is capital D, that is 550 mm, and we have provided 4 bars of 16 mm dia. That means we are at the bottom will provide 4 bars of 16 mm dia. So this detailing has to be given to the site. As per this detailing, they are going to do the construction. Next we will go to another problem, that is in this beam, size of the beam is width is 230 mm, depth is 400 mm, that is effective depth, with FCK is equal to 20 and Fe415 steel we have. In this problem they have given the strain in the steel. Strain in the steel is 0.009757 mm, and concrete attains a maximum strain. Maximum strain in the concrete we have seen in the assumption, that is 0.0035. That is the maximum strain in the steel. So maximum strain in the steel and strain in the concrete as well as strain in the steel they have given. Based on this, we have to calculate what is the area of steel required. So what we can do, so this is the data. B is 230 mm, D is 400 mm, FCK is 15, Fy is 415. Now ES, strain in the steel, it is 0.009757. Strain in the concrete, it is 0.0035. So based on this, we have to calculate what is the area of steel required. So we will try to draw the strain diagram. So already this we have done in the derivation. So strain in the concrete, it is maximum. They have said concrete attains 0.0035. So therefore epsilon C will be 0.0035. Then next they have given this epsilon S value, that is strain in the steel, that is 0.009757. So based on this, we have to calculate the steel required now. So we will take similar triangles, that is XU, or if you draw the simplified diagram, so this is XU, this is the XU we have, this is XU we have, this is nothing but total effective depth D we have. So now epsilon C is 0.0035, this is the triangle we have, this value is 0.0035 we have, 0.0035 we have. Then next this value, so same thing if you drop it downwards. So this value is nothing but 0.0035. This value is 0.009757. 0.009757, 0.0035. So based on this similar triangles, what we can do, we can write this, that is XU divided by this, that is XU, what you can say XU, that is XU, what you can say XU, that is equal to epsilon C. Then next is this total D divided by this distance, that is epsilon S plus epsilon C. So if you cross multiply this, you will get XU is equal to epsilon C divided by epsilon S plus C multiplied by D. So in this formula, we will try to substitute now this is known to us, these things are known to us, multiplied by B, D, you will get answer as 105.6 mm. This is nothing but the depth of the neutral axis. So based on this, we will try to calculate the moment now. 0.36 FCKB into XU, D minus 0.4 to XU. So you substitute value of XU, that is 105.6, will get answer as 46.64 kilonewton meter. This is the moment resisting capacity of the section. Then next is that we have to calculate the area of steel. So again same formula, m is equal to 0.87 f of I into st into d minus 0.4 to xu. Same way, once again, if you substitute, if you simplify this, everything is known to us except this ast, if you cross multiply, you will get answer as 363.22 mm square. This much area of steel is required. So this much area of steel is required. If you want to calculate number of bars, you can provide different number of bars, like 2 bars of 16 mm dia you can provide. So 2 bars of 16 mm will be like 200 plus 200, that is 402 mm square will be the bar, diameter of the bar. For given diameter of the bar, that is the area of steel. Next we will go to another problem, that is a RCC beam of rectangular section 300 mm wide by overall depth 100 mm wide by overall depth of 850 mm is reinforced with 4 bars of 25 mm dia on the tension side. So here you can see they have given B is 300, overall depth, this is nothing but capital D, that is 850 mm. It is reinforced with 4 bars of 25 mm dia. They have given on the tension side. Effective cover, that is 50 mm they have given. The next is find the ultimate moment of resistance of the section. FCK is 20, FI is 415. Next, means first thing is that they have said us to calculate the moment of resistance. M value you have to calculate. Then next what they are asking is find the additional reinforcement required to make this as a balanced section. So first we have to check whether it is over reinforced or under reinforced. Based on that we have to calculate, so as to make this section as a balanced section, how much additional reinforcement has to be provided, that has to be calculated. So this is the given data. B is equal to 300, overall depth is 850 mm. We have to calculate the effective depth. How do you calculate effective depth? Overall depth minus of clear cover, effective cover. So effective cover also they have given, that is 50. So therefore effective depth will be 800 mm, small d. FCK is given, F of I is given. Then next is area of steel is also given. So they have said we are using 4 bars of 25 mm dia. So we have to calculate what is the area of steel. So how we can calculate? Pi by 4 into d square. This is nothing but area of 1 bar. So multiply by 4, we will get 1964 mm square. This much area of steel it is being provided. The next is we have to calculate for case 1. First we have to calculate, we have to check section whether it is under reinforced or over reinforced, and we have to calculate the moment. So first let us calculate this neutral axis depth. So same formula, 0.87 f of I AST divided by 0.36 FCK into B. So AST just now we have calculated. This f of I, FCK and B are already given. So depth of the neutral axis is 328 mm. Then next we know the limiting value, that is XU max. This is being given in the code book itself, that is 0.48D for FE415 steel. So XU maximum depth of the neutral axis, if you calculate, it is 384 mm. XU what we got is 328 and limiting XU is maximum XU is 384. This is less than this. So XU is less than XU max. Therefore section is under reinforced section. Then next we can calculate the moment. So 0.36 FCK into, so XU value just now we have calculated. If you substitute, we will get moment as 470 kilonewton meter. This is the moment which is going to come. Then next what question they are asking is, in the second case, if you for a balance we have, as it was a under reinforced section, we have to make it as a balanced section. So if you want to make it as a balanced section, first we'll try to calculate what is the limiting moment. So limiting moment formula is 0.138 FCK BD square for this Fe415 steel. So if you substitute this value, so limiting moment is 529.92 kilonewton meter. Then next is MULIM, so that is equal to 0.87 F of phi into AST-LIM into D minus of 0.42 XU. What you can do, you can calculate the limiting moment now. We can calculate the limiting area of steel. For this moment, so what is the area of steel required? If you simplify this equation, you will get AST limiting as 2297 mm square. So if you want to make this as a balanced section, so area of steel required is 2297 mm square. But what we have done is that we have already provided a steel of 1964. How much additional has to be provided? How much additional? 2297 is required for limiting moment minus 1964. So that is additional reinforcement required will be AST-LIM minus AST. So 2297 minus of 1964, that means 333 mm square of area is required. So this much area of steel is required so as to make this as a balanced section. Next we'll see another problem, that is we have a RC beam of width 300 mm, overall depth, they have written overall here, that means this is nothing but capital D, that is 550 mm. It is reinforced with 4 bars of 16 mm dia, effective cover of 50 mm. If it is given, you can take this value. If it is not given, you can assume this value as 50 mm and you can proceed. Next is they have given the beam is simply supported over an effective span of 5 meter. The beam is simply supported. So for example, now this is the beam we have. This is the simply supported beam we have. So here we are going to have the load, and sections of this size is 300 by 550 mm. 300 by 550 mm we have, and 4 bars of 16 mm we have. So if you take one beam, this is the cross section, we have 4 bars of 16 mm dia at the bottom. If you provide this section and if you provide 4 bars, so how much load we can put on that beam? So what is the maximum load carrying capacity of the beam? So that is what they have said us to calculate. So find the maximum load carrying capacity of the beam inclusive of self weight. So you can use grade of concrete as M20 and Fe415 steel. So now in this question they have reversed now. In this what happens is that they have given on simply supported beam, they have given the sections and they have given the bars. They are asking us to calculate how much maximum load this beam can carry. So that has to be calculated. So what we can do, B is given to us, D is given to us. Then next is they have given us the overall depth. We have to calculate the effective depth. So overall depth minus of effective depth. Overall depth minus of effective depth. If you effective cover, if you do, you will get it as effective depth. So therefore 550 minus 50, that is equal to 50 mm. Then next is they have given 4 bars of 16 mm dia. So if you calculate that area of steel, that is pi by 4 into d square multiplied by 4, you will get answer as 804. So this much steel is being provided, and they have given span as 5 meters. For this given area of steel and for this given section, how much movement it can carry, that we can calculate by substituting in this formula. So 0.87, F of I we know, area we know, D we know, so everything is known to us. So if you substitute here in this equation, so you will get the moment. So 129 kilonewton meter. So it is going to carry a moment of 129 kilonewton meter. So what they have done is, so they have given the beam now to the UDL on this. So now we have calculated the moment. So how do you calculate the moment? So for a simply supported beam, WL square by 8. We are going to get the moment. So now moment is known to us. You cross multiply this L is nothing but the span. So that also we know. If you cross multiply, you will get this WU. that is equal to, you cross multiply 8 mu you have divided by this L square, it will come at the bottom. So therefore W is nothing but the load. So that load will come to know. If you substitute in the equation, you will get answer as 41.28 kilonewton meter. So always we are calculating for factored load. So for factored load means we can put a factored load of 41.28 kilonewton meter. But we have to calculate the working load. So from this working load, generally in the previous problem we have seen how we had done factored load. We used to multiply by factor of safety. So this is nothing but, for example, now we have factored load now. We have to calculate this working load. So how to calculate working load now? We are going to divide it by factor of safety. So therefore W is equal to this factored load divided by factor of safety. If you are going to do, you will get answer as 27.52. So this much amount of UDL we can put on a given beam section. This is nothing but the working load. So you can see this is also similar problem which was asked in the previous question paper. You can refer this problem and you can try to solve on your own. So again same thing, AST we have calculated, moment we have calculated. Based on that we have calculated what is the factored load and what is the working load. So this much working load we can put on a given beam section.